So far you've learned that a workflow is a graph consisting of a large number of batch jobs and files, and a workflow management system dispatches those jobs into a batch system. What we're missing now is a way to represent that workflow in a language form so that you can write programs at very large scale. Now, there are several ways of representing workflows. We'll start with one that's very simple. It's based on the old idea of makefiles, and then we'll survey some other options out there. The makefile is a very old idea in computer science, and it goes back to the 1970s. It was invented by an engineer named Stu Feldman. And originally, makefiles were used to describe all of the steps necessary to build a program from source all the way to an executable. And that's usually the context in which we see them, but we don't have to use makefiles just for building programs. We can use them for any kind of task that has multiple steps with files in between those steps. And so here, I've got a graphical view of a simple application that consists of reading a file with a program called split.py, splitting it into 3 pieces, running a simulation, and then taking those 3 pieces and joining them together. We can take that graph structure and we can represent it in the make language, describing what to do. And so each rule here describes an individual step to carry out. Now, with this language, using traditional make, we can run a set of applications in order on one local machine. But we want to do something more powerful. We want to take a very large graph and run it on a distributed batch system. And so I'd like to discuss Makeflow, which is a tool invented by my research group here at Notre Dame. And Makeflow combines the idea of make with the concepts of workflows. So Makeflow is a workflow management system that reads in a DAG structured workflow and is able to take each individual job in that workflow and dispatch it to different kinds of execution engines. It can run it locally just like it was a traditional makefile, or it can take those jobs and submit them to the Condor distributed batch system, or to a cloud service like Amazon, or to another service called WorkQueue, which we'll look at in the next sequence of lectures. Makeflow gives you some portability across these different batch systems. It's nice in that you can express your workflow in a neutral way using the plain old make language, and Makeflow will automatically transform things as needed to talk to these different batch systems. Makeflow allows you to run things in parallel without expressing so much parallelism that you might break the batch system. It gives you fault tolerance at multiple scales, so that if a task fails or does something unexpected, it can stop and retry it, or inform you of what might have gone wrong. And it also gives you some data and resource management so that you don't exceed the storage capabilities of the site that you're using. That's the idea of Makeflow. Let me tell you a little bit more about the syntax in case you're not familiar with traditional makefiles. So, the syntax of a traditional makefile is that for each job that you want to run, you have to specify the output files that it's going to produce, and then a colon, and then the input files that are going to be consumed by that program. Now, maybe that seems a little backwards to you, and that's okay, but you can read it as these files come from those files. Then, below that statement of the files, you give the command that you want to run as just a plain old Unix command line. And that command line better produce those output files from the input files that you stated. So this chunk together here is called one rule in a makefile. Let me give you a concrete example of one rule in a makefile. Suppose that I have an application called sim.exe, and the command that I want to run is sim.exe on some input file with a parameter of 50 and send some output to a file called output.txt. That would be expressed graphically as, here's this process, here are its input files, and here are its output files. Now we have to be a little careful because sometimes Unix applications have implicit dependencies. That is to say, there are files that they expect to read, but we don't actually mention them on the command line. You'll remember from an earlier lecture that this is a bad idea, but sometimes it happens, and so we have to be able to accommodate it. In this case, sim.exe is expecting to read implicitly a file called calib.dat. Maybe that has some calibration data. So what we have to do in our rule is specify the output files it produces as well as all the input files it depends on. And here we have output.txt is produced by input.data and calib.data and sim.exe. You know, we have to specify the executable as a dependency as well, because that's the only way that we'll know that the simulator needs to get to the place where it's going to execute. So here's our complete rule: the output file, the input files, and the command necessary to generate it. Now, this is the most important thing you have to remember about Makeflow. You have to state all the files needed by the command, which is to say, You have to really understand what's going on and state those things explicitly. If you don't state them explicitly, Makeflow won't have enough information in order to generate the proper batch jobs for execution. Now, one rule isn't enough. If you're going to run a whole lot of things, then you're going to have a whole lot of rules in your makefile. So suppose we have a makefile here to run 3 different simulations, and we put it in a makefile called sims.mf. Well, then for each simulation I want to run, I would have a different rule. And for each rule, I would send the output to a different file, and perhaps give different parameters to that command so that each output is different. Now, obviously, if you're going to have a million rules, you're not going to sit there and type them all in manually. A common practice is to write a script in your favorite programming language which will print out the makefile, and then you're ready to go. So now that you've written your makeflow, how do you use it? Well, suppose we have a simple makefile here with one rule. To actually execute it, you'll enter the command makeflow and specify the kind of batch system that you want to dispatch the job to. In this case, we want makeflow to send jobs to Condor, so we'll say -t Condor. And we'll give the name of the entire makeflow to run. Now what makeflow does is it looks at each rule in turn and generates the detail of the Condor submit file necessary to run it at the local site. And there could be a whole lot of details in that. You'll remember from previous lectures that for a Condor job, we have to specify the universe and the executable and the arguments and the input and all that stuff. You don't have to worry about that because that's all going to be generated automatically from the makeflow file. So makeflow generates that automatically and then sends it off to the Condor batch system in order for it to be executed. Now, makeflow allows for portability. So perhaps Condor isn't the thing that you want to use. If instead you want to use the Torque batch system, well, it's the same idea. You're simply going to specify that Torque is your option. And now Makeflow will generate a different set of details appropriate for the Torque batch system. In this case, it would be a little batch script with some options at the top and then the command to be executed. So Makeflow generates that behind the scenes and then sends it off to the Torque batch system to be executed. So in this way, Makeflow gives you portability. For each rule, you specify it in a generic way, and Makeflow is responsible for transforming it into the local batch system. It's often useful to get a graphical picture of your workflow. And so this example that I shared earlier is in fact just some output from Makeflow. We have a tool called Makeflow Vids that will produce, using the dot tool, a graphical representation. And this is often handy for debugging, just to run off the picture of what you're doing. It can help you figure out if you have accidentally an extra dependency or perhaps not enough dependencies when something goes wrong with your workflow. Makeflow is just one of many workflow systems out there, and it's based on the traditional make syntax. But there are other workflow systems and ways of representing a directed acyclic graph of tasks. A classic is DAGMAN, which is in fact part of the HT Condor project, and DAGMAN stands for Directed Acyclic Graph Manager. And the idea of DAGMAN is that if you've already written your jobs in the form of a Condor submit file, then you can write an extra script that will simply describe the relationship between these jobs. So for example, if I wanted to run job A and then job B and C simultaneously after it, then I would write a DAGMAN script like this, which says here's job A and B and C, and then A is the parent and B is the child, so that explains that relationship there. And A is a parent and C is the child, explains that relationship there. So DAGMAN is very effective at expressing relationships between jobs, but note that it doesn't say anything about the data. So this only works under the assumption that A is producing some files, which then B is going to consume. So you have to state all that stuff explicitly in your Condor files. But if your objective is to use Condor in the first place, it's a perfectly good option. Now that's a scripting approach. There are other workflow systems that use a more graphical approach. So another instance is called the Kepler workflow system. And this uses a graphical editor to construct a variety of nodes and make dependencies between them. It also allows for control flow, so you can write if-then statements and loops. And this is a highly effective tool to use if you want to use graphical construction. The Pegasus workflow management system is highly effective at managing large DAGs that move data around the wide area. With Pegasus, you generate a DAG in an abstract form known as DAX, D-A-X. And this is an example of the DAX language here. And in DAX, you define jobs, and just like any other language, they have inputs and outputs and define a command. But they refer to files abstractly. And now what you do is you use Pegasus to process this DAX and produce a concrete workflow that has been specialized for your local environment and has made decisions about where to pull data from where to move it from, and how many jobs to run concurrently, and it's typically used to feed into Condor's DAGMAN. Pegasus is widely used in the scientific community for writing DAGs that have a very large amount of data movement. Another option is the Swift parallel scripting language. Now, Swift is a little different in that you don't express a DAG directly, but instead you write in a programming language that has familiar ideas like functions and loops and conditionals. And so for each program that you want to execute, you define a simple function, specify where its input and output files go in a way that is parameterized, and then you can write loops over that function that will generate a large number of things. So Swift is highly effective at generating large workflows that are hierarchical, nested. Particularly if you have a large number of simulations with many parameters, it's a very easy way of specifying what you want to be done. A more recent development is the Common Workflow Language, and the developers of the CWL have observed that there are many different workflow systems out there with common properties but different languages. And the hope is that by defining language in a technology-neutral way, it should be possible to write a workflow using a YAML syntax and then automatically translate it or have it read by a variety of workflow systems. This language is still in the early phases of development, so we'll see if it takes off. So you've seen several different ways of representing a graph-structured workload. They are all at some level logically equivalent, but each workflow management system has different strengths in terms of scalability and portability and data management. These systems continue to evolve over time, each optimized for different use cases, but the underlying concepts remain the same.